So let's do example 4.2, part of lecture 4.2 on half-wave rectifier. So given the circuit shown with the voltage source being a cosine with amplitude 3 and period of 1 second, what is the output VR, the voltage across the resistor? Explain why this might be called a half-wave rectifier. Let R equal 10 ohms. So there are sort of different ways we can try to split up this problem, but I want to follow primarily the procedure that we outlined. Okay, so there's only one diode, and that's kind of nice because if there were more, it would be a more involved problem. But the process would be the same. We're trying to follow the same process that we would have followed with a larger system. So if we're going to begin at the initial time t0, time equals 0, then let's just think about, let's just try to reason our way through for just a moment. A cosine wave starts off at time equals 0 at 1, right? So cosine of 0 is 1, so 1 times 3 is 3, so 3 volts is applied. And we have a diode here that's going to be, just to guess, just at this point, just guessing, what do you guys think? Do you think that diode is going to be in forward bias or reverse bias? Forward bias, probably. We're going to drop voltage across it in the direction that it wants to flow current. So it's probably going to flow current. There is a threshold you have to reach before it'll start to flow that current, but that's the thing that we have to check. But probably when you've got 3 volts, it's going to be fine. When you get lower, it's going to shut off at some point, right? So as we get lower and lower, that diode will shut off. So that's what we're thinking is going to happen. It's going to be on when we're in the positive part of the wave. At some point, it's going to get low enough to shut off, and then it'll be 0 volts coming out, and then it'll be back on. That's what we're kind of thinking, right? Now, let's go through methodically, though, and do the analysis, because this is easy to do with one diode, but harder to do when you get more diodes. So let's start out by replacing the diode with the diode model that we're going to use. So replace the diode with the we called it, I think we called it the piecewise linear model, which I actually have a note about to mention. This diagram, remember how I was like, oh, this is wrong in your notes? Yeah, no, it was right in your notes, and this is wrong. So go back to figure 4.5. We don't have a voltage gain in here, we have a voltage drop. So it should be the large cell and then the small. And so it should be plus and then minus. So it is 0.6 volts, it just goes the other way. Okay, so yeah, that's important to note. But we're going to take this now, this piecewise linear model, and we're going to plop it in to the circuit where that diode is, right? That's our plan. So back down here, we can redraw our circuit plus minus with the ideal diode and then the voltage drop, the constant voltage drop, of 0.6 volts. And so plus, minus. And then a resistor RD. So that's our circuit that we're going to analyze, where this is the original resistor R. This is, of course, Vs. So we want to do our circuit analysis of this circuit with, remember our method is to ignore what the diode is going to have as its elemental equation at first, right? So we start off, and I think this was like step 3. Step 3, proceed with the circuit analysis of chapter 2, ignoring the elemental equation for the ideal diodes. And we're going to come up with a system of equations that is missing one equation, okay? Well, one for each diode. Yeah?
Why do we assume the voltage drop is 0.6 volts?
It's very, very, very common that almost all diodes have the same. And so there are, and you could have exceptions, but almost all diodes have a 0.6 volt drop. You could, so for a very specific one, you can measure this, which is probably the best thing to do in a given case. But for most diodes, it's very, very close to 0.6 volts. So it's nearly universal, but you could have one that's 0.7, you could have one that's 0.5, but it's usually 0.6. Well, and I should say this is the model, right? And like it's very close to 0.6 volts, but so if you go back up to our the nonlinear model is a little bit closer to reality. So notice how like the nonlinear model, if we zoom in here, nonlinear model starts to rise before 0.6 volts, and so it's not a perfect transition, but it's around there. It's a pretty good approximation for most cases. There's always, when you do a piecewise linear model, you have to choose some cutoff, and that's a very common one to choose for this. And it's pretty good for most diodes. Okay, so this is our model, and we want to do the step 3 analysis here. So we're going to do our circuit analysis, assuming, or I shouldn't even say assuming, ignoring. We're just ignoring the diode, the ideal diode elemental equation. And we're going to use the method of assumed states to get that last elemental equation, but we want to do the circuit analysis first. There are some people who teach this method where you assume the states and then draw your circuit fresh and then do the analysis, and then assume a different state, draw your circuit fresh, do the analysis, but that's a lot of extra work. So I think you should do the analysis once and then make your state assumptions, which is just essentially just adding one equation for each diode. So that's what we'll do. So we'll do the circuit analysis. We'll do our usual process, the elemental equations. So let's do our passive elements that are ignoring the diode are going to be the resistor R and the diode resistance RD. Okay, so R is VR equals IR times R. And VRD is also just equal to IRD, RD. Just Ohm's law in both cases. They're both just resistors, right? So this does bring up the question of RD. What is the diode resistance? Remember that the diode resistance is the reciprocal of the slope here. So maybe I'll draw it on this side. So 1 over RD. And this is kind of a tough question in a lot of problems, but there's the question of what is our operating point really? So what is the diode voltage going to be most of the time? I would say for this circuit, it's very unlikely that we're going to have a reasonable value for this that's accurate over the whole range, because we're going to have a sinusoidal input, right? This AC input is going to vary significantly across it. So the diode voltage is probably going to vary fairly significantly. So we don't expect to have a great stable point here. It's going to go from 0 to something non-zero. Okay, so we've got to choose something if we're going to use this piecewise linear model. And a common thing to do is to choose a sort of intermediate value when you don't have a great value to go with, because they're kind of all over the place. So if we chose RD is equal to about 0.2 ohms, then if you took the reciprocal of that, so this is 2/10, so this would be like 5, right? So 5 would give you for 0.1 run here, you would get a rise of 0.5, right? So that's not terrible when you're looking at the low end of voltage. We're only going to put 3 volts across this thing max, right? The max total voltage we could ever get if the other resistance was not a part of it would be 3 volts. So we're not going to be putting huge voltages across this thing. So that's a pretty good place to start, is to start with something that's like, okay, pretty pedestrian, like sticking to this sort of low end. We're not going to get to really high voltage drops. So we'll try that. We'll stick with this. It's good to, at the end, go back and check, like how close was I to the operating regime given the solution, given the assumption that I made, how close was I? And you can iterate a little bit if you want. So you could get a solution and say, wow, the current was actually like 10 amps that was running through this thing, and my diode voltage was out here like above 0.7, and so I needed to have a much more significant slope. That would be reasonable to do, and then go back and iterate in the problem. In this problem, this isn't going to change it significantly. Our results will be pretty similar, and we'll see that emerge in the solution. So, okay. Great. So we're going to use that RD. If that feels unsatisfactory to you, that's kind of what you get with these piecewise linear models. They're not great. They're not very satisfactory, but they do actually show you the broad operation of the circuit. Really what you need is the nonlinear model to give you the most fidelity to the real operation. So it's as good as we can do, but it's still not perfect. So we have our 2 elemental equations. We have our KCL equations as well. And I think at this point we're probably pretty comfortable just saying, okay, everything in series has the same current, right? As long as we draw our signs the same way. So if we draw our signs all dropping that way on our elements, then all those currents are equal to each other. We could do nodes in between, but just say all those currents are equal. So that means that our node, our diode current is equal to our RD current, which is equal to our R current. So that's two useful equations. We are interested in ID, IRD, and IR. We could also talk about the current from this sort of imaginary source, and we could also talk about the current from the real source, but those aren't of interest to our analysis, so we're not going to write them down. Okay, so then we've got KVL. And we've got one loop, right? So there's one KVL equation. So VD, the diode voltage. And then we've got, wow. We've got plus 0.6 volts. And then we've got plus VRD. And then we've got plus VR equal, we've also got VS, right? So then minus VS equals 0. Why did we do minus VS? It's a gain in voltage if you go around clockwise, right? And we were using drops as positive, so. Drops are positive, gains are negative. So we dropped all the way around until we hit VS, and then it was a gain. Somebody had to gain around that. So VS is the one that gains. So this is the KVL equation. There are elemental equations, our KCL equations, and our KVL equation. So this is one equation, two equations, 3 equations, 4 equations, right? Because this is 2 equations, actually. And then 5 equations. So 5 equations, we have 3 elements, 3 passive elements. So we have 1, the diode, and then 2 resistors. So that makes 3 passive elements, and so 6 unknowns, right? So the one equation we're missing, so we have 5 equations and 6 unknowns. The one equation that we're missing is the one that we left off intentionally, the diode, the ideal diode equation, which can be either on or off, right? And that's the point where we have to do our method of assumed states, right? So now we've reached kind of the end of the road in terms of analysis. But what we can do, and this is the thing that I do suggest that we do up here, is to simplify to the extent possible. We know we can't solve for all of our unknowns, but we do know that we can simplify this. So there are going to be 2 really interesting equations that we're going to want to write down, and then there are some auxiliary ones that are going to be interesting to us. So the first is we want to know what VR is, right? That's what we want the solution for. We want VR. So VR is our goal, and we want to write it in terms of the voltage drop across the diode, so VD, and alternatively, we want to write in terms of the current through the diode, ID, because when we do our method of assumed states, those are the 2 variables that we get assigned, okay, in that assumption. So when we assume that the ideal diode is off, then we're assuming that the current ID is 0, right? When we assume that the diode is on, it's like conducting, it's a perfect conductor, so VD is 0. So we want both of those solutions. And we can do that. We can do that without having VD and ID. So those are 2 equations we want to develop. The auxiliary ones are going to be the checks, right? The way that we're going to check to see if our assumption was correct is to see if we have assumed that ID is 0, then we assumed that the diode is in reverse bias, right? So we assume that the VD is negative. And so we want an equation for VD as well. So we would like these different assumptions depending on what we're checking. Okay? So let's derive those expressions, and then we're done with analysis. All we have to do is essentially plug in zeros places and then see what happens. So that's what I think we should do. So simplify. Simplify. So let's first find VR. The easiest one of those equations that I outlined to solve for is to find VR in terms of ID, okay? Because VR is equal to IR times R from this elemental equation, right? And we know all of the currents are the same. So IR is equal to ID. So in other words, VR is equal to ID times R. And that's it. That's one of the equations that we want to know. So this is our solution. And when ID is 0, we know VR is 0. So that's that's an immediate thing that pops out. But we don't want to just stop there. We want another version of VR in terms of VD. Okay? Because in the other case, we're going to assume that VD is 0, right? So we want another expression in terms of VD. So let's take this as equation 1, we'll call it. Let's also develop a further equation. Let's say, okay, it's also equal to IRD times R, which IRD is, from its elemental equation, is just VRD over RD, right? So we have R over RD times VRD. Okay, from KVL, we can write VRD. So it's actually funny. I'm just wondering. Yeah, we would have VRD. Okay, good. So from KVL, we can eliminate VRD, right? So VRD is equal to VS minus 0.6. I'm going to say we're going to write all of our voltages in volts, so we don't have to keep writing V. Minus VD minus VR. Right?
I lost from VRD, not VR, right?
No. Because we just substituted in for VR. So we took VR, we solved this for VRD. And if we solve that for VRD, it's equal to VS minus 0.6 minus VD minus VR, right? And then we just took that and inserted it in there and got this expression. So we've got VR on both sides, right? So if we solve this for VR, we would want to add R over RD times VR to both sides, factor out VR, divide whatever's left onto the other side, and we're left with VR equals R over RD divided by 1 plus R over RD times Vs minus 0.6 minus Vd. Or a little bit simpler would be to multiply numerator and denominator by Rd to get R over R plus Rd times Vs minus 0.6 minus Vd. So this is an expression for VR in terms of Vd, right? So that one's going to be very useful. We'll number that equation 2. And we could just go on right now because these are the two solutions, but in order to check if they're valid or not, we're going to need solutions for ID and VD as well. So why don't we try to develop... I'm on the fence on this. If it's easier to develop the equation before or see the assumption and then develop it. I think it's easier to develop the equation before. So we'll develop the testing equations too. So we need to solve for ID and RD, and we want them to be, ID and VD, and we want them to be in terms of VR and, well, a VR would be ideal. So let's see what we can do. We see that the first one's pretty easy. If you want to know what ID is, and you have VR, from equation 1, we know that ID is just VR over R, right? Okay, so that one's a nice check equation. So we'll call that equation 3. And now we want a VD equation, and the V's are harder, right? So we can solve this this one down here back for VD. So if you wanted to solve for VD, so it's not too bad. So you just have to you're gonna have R plus RD divided by R times VR, and then you're going to, this is all going to be negative, I guess. That's negative. And then we're going to have plus Vs, and then we're going to have minus 0.6. I just solved 2 for VD. So this will be equation 4. Okay. So, awesome. Now we're ready to start assuming states, okay? So we're going to guess wrong today in class on our first guess, just to see what happens, but this is not what you want to do, okay? So it's a little bit tricky because we typically want to look at this and say, oh, okay, we think we're going to be at initial time when the cosine wave is positive. We're probably going to have forward bias, and we should assume that the diode is on. So that's probably what we should do. But we're going to make a mistake on purpose just for demonstration purposes. We want to see what happens when we guess wrong. Okay? I don't want you guys to always guess wrong on purpose. I just want you to do it for this exercise to see what happens when you do guess wrong. Guessing wrong is totally fine. It's just not what you would prefer to do most of the time. So let's, for the sake of demonstration, for demo only, we're going to guess wrong. Which is to say, we're going to guess that at the initial time, so at t equals 0, we're going to guess that the diode is off. So let's see what the implications are of that. So if the diode is off, you can go back up to, if you'd like, the procedure that I laid out. If we say that the diode is off, that's this case, and we need to set the current of the diode equal to 0. And the assumption we're going to need to check is that it is in fact in reverse bias, that VD is less than 0. Okay? So that's the next step. So let's do our ID equals 0. So this is our, so we get our final elemental equation, ID equals 0. Okay? So now we get our last elemental equation we can solve for everything. But we've already solved for the things that we want in terms of ID, so we don't have to go through that algebra multiple times. So ID equals 0, so we say from equation 1, we called it, we see that VR has to be 0, right? So that's the solution. VR equals 0. So that's the solution. And if it checks, if our check works out, then that's the correct solution. So it's almost best to say equals 0 question mark over it. Maybe it equals 0. Let's find out. Let's check the condition. Okay. So the condition is that we have to be in reverse bias, right? We have to check that VD is less than 0. Okay. So if we come back here and we plug in our VR, which we just solved for, we're assuming it's 0. It's going to be so check. VD is equal to 0, because VR is 0, plus VS, so at the initial time, that's 3, right? Cosine of 0 is 1. 1 times 3 is 3. So that's 3. And minus 0.6 volts, which is equal to 2.4 volts, right? And so our check was, though, that VD had to be less than 0, right? Is this less than 0? No, it's not. So, which is, we could write maybe not less than 0. So therefore, it fails the check. In other words, the diode being off is not a solution to this problem. At time equals 0. Okay? So we have to go back and change our assumption. Okay? We only have one diode to change, so it's kind of nice. We just flip it, right? So we're going to be right on this one. We have to be. So otherwise, I don't know, everything's broken, and we can all just go home. So now, so guess correctly. So at time equals 0, the diode is on. is on. So when we assume that the diode is on, we assume it's a perfect conductor, and therefore the voltage across the ideal diode is 0, right? So that's our, in this case, that's our sixth elemental equation, our final equation for solving the system. But once again, we've already solved for what we need. We need VR in terms of VD. So from the second equation, equation 2, we have that, so equation 2 is this guy. We plug in VD equals 0, right? So we say whoops. I think we can do it up here. VD equals R over R plus RD times, if this was VS minus 0.6 minus, well, VD. I wrote VD equals. This is VR equals, right? We're solving for VR. But VD is 0, right? We just assumed that. VD was 0. And if you plug this in, so R is 10, RD is 0.2, so 10 over 10.2. That's where we see that RD is not a huge factor, even if we're a little off on this. As long as your load resistance is significantly larger, it doesn't tend to matter that much. And VS is going to be 3 minus 0.6. So what do we end up with for VR? It's like 2.4, 2.3 something. 10 divided by 10.2 times 2.4, 2.353. 353 volts. So, but it's the question mark, right? Because we have to check. I mean, by process of elimination, we kind of have already checked, but let's do our check anyways. We need to check that ID is in fact positive. Okay, that's the check. If it's in forward bias, it's got to be conducting current through it in the forward direction. So we solve for ID from, I think it was 3. So we use 4. I should have said we used 4 here, right? 4 got used there. So from 3, we know that ID is equal to VR over R. And if VR is 2.353, R is 10, then this is equal to 0.2353 amps, which is greater than 0. So that checks, right? So now we believe our solution that VR is 2.353 because the solution checked. And that was the only diode, so that was the only check we had to make. If you had multiple diodes, you have to check all the diodes. Okay, so we got it. This is only at time equal to 0. So now we need to extend that. We need to extend it in time. So we've already got what we need for that. The steps that we did, plugging in time equals 0, all we need to do is just not plug in time equals 0, just leave it as t, and see when our assumption is no longer true. Okay? So now we say, let's continue to guess correctly because we already went through this, right? So we're going to say back to our VR solution. So VR of t is equal to r over r plus rd times, and now Vs, we'll just plug in what Vs is. 3 cosine of 2 pi t. Okay? Minus 0.6 minus, so minus Vd. Yeah. Minus Vd. Well, actually, when we've done this, Vd is assumed to be 0, right? Because we're assuming that the diode is on. So this is the solution, and it's is valid until ID equals 0, right? Because ID has to be positive for this to be true. So until ID is 0, this is the solution. So let's find out from the check. So from 3. So from 3, we know that ID is equal to VR over R. And so what we need to know is how long VR, so if we need to know when ID equals 0, we need to know when VR equals 0, right? So ID equals 0 when VR equals 0, right? So VR equals 0 when 3 minus cosine 2 pi t, not 3 minus, 3 times. I don't know why. 3 times cosine 2 pi t minus 0.6 equals 0. Solving for t, this occurs when t is equal to whatever the, what does that work out to be? It's like 2.2 something. I had somebody with fast calculating skills this morning in class. You guys are falling behind. Sorry? There it is, 0.218. 0.218 seconds. So that solution is valid from time equals 0 to time equals 0.218 seconds. And then it's not valid, right? Because this assumption fails. So we actually know in this case what the solution is going to be, because it's going to have to flip to the other one, right? It has to flip to the other solution. But the other solution is really easy, right? The other solution is that VR is just ID R, but ID is going to be 0. And so VR is going to be 0. So it's going to look like a cosine until time is equal to 0.218. And then it's gonna look like a cosine that's offset by 0.6 volts. And then it's gonna flatline. And then once the voltage source comes back up, it will switch back to on again. Okay? And so let's look at the graph and see what happens. So the input is the blue line, Vs, and the output is VR. So the red line is what we just solved for. So we just solved for this portion, Well, actually, we solved for, this is time equals 0 on this graph, so we just solved for this interval, right? And then we said, okay, then it turns off after 0.218 seconds. And then it's going to be off. We didn't solve for when it turns back on, but we could with essentially the same procedure and see that we would get a repetition of the same waveform over and over again. So this analysis is pretty involved, right? It kind of takes a while. It's pretty involved. But if you've got DC sources, you don't have these. I did it's a simple example in terms of the circuit being simple, but it is an AC input, which is actually kind of hard to do with diodes. So we have to be methodical, but we can do it, right? Okay, that's all I've got for today. I'll see you guys on Monday. And I declare a winner of the vote soon, so.